All right. Let me just calibrate this camera real quick. Okay. So we will be touching up on one last thing in 9.1 and then moving on to 9.2, which is vectors. Let's talk about the region. Describe the region in R3 parameterized by the given conditions. Okay. So notice that this is an inequality, and it is supposed to correspond to something geometrical in R3. What if I just set this piece of this equation here to the 1? Because it can't equal it, correct? Also, what if I set this piece of the equation equal to 9? Because it can equal it, right? Whatever this geometrical expression is, whatever this phenomenon in R3 is, it at most will assume this and at least assume that. But first we have to find out what is this in R3. Can anyone tell me? Is it a disk?
Oh, it's not a sphere because it's not. Oh, so it'd be a cylinder.
Cylinder. Why is it a cylinder?
Because it's an unbounded z.
Yes, because we haven't specified z. It ranges whatever values it wants. Z can be anything. So it does create a cylinder, a cylindrical shell. So over here, here's my z, here's my x, here's my y. I'll start with the inner region. This inner region will create a cylinder going to infinity of radius equal to 1. This is the inner one. And then you're going to get a larger one over here. And it's going to infinity as well. They're infinite cylinders. Okay, but this one has a radius, what do you think? 3. Okay, so in R3, this inequality is going to highlight not what's in here, but what's everything out here, all the way down the cylinder. You see what I'm talking about? So, yeah, it's like a tube within a tube, but it's solid on the outside, all the way up to the rim of radius 1. So we think of this kind of like a solid region instead of just a shell. It's no longer a cylindrical shell because this function assumes all the values in between that. Next, let's talk about something like this, this inequality. You can tell me what this symbol means in math. Typically used shorthand right here for such that. Get tired of writing such that, such that, such that, such that. We get tired of writing it. So we just create a symbol for it. It's like a backwards epsilon. Okay, what is this? Applying kind of like the same reasoning here. This is sphere, correct? Yeah, okay. What happens when this part is equal to that? It's a sphere of what? Radius what? 2. What happens when this equals this? It's a sphere of radius what? 6. So now let's not ignore this little z over here. What does this z imply? Yeah, it's for positive values of z. All right, so it's just going to be the upper hemisphere of these two spheres. All right, so this is very difficult to draw. I'm just going to do my best here. Okay, but it's just a upper dome, if you will. Maybe I'll just delete that so it looks more like a sphere here. It doesn't go down below this XY plane because then Z would assume values less than 0, right? So it's just the upper domes, the upper hemispheres. And it's the region from this lower radius 2 hemisphere to radius 6 hemisphere. So it's this shaded region in between there. Very much similar to this. So you guys are gonna need to get used to thinking about problems like that. Okay, moving on to vectors. Okay, mathematicians and vectors like to talk about vectors differently, but they're really talking about the same thing. Calculus 3 was invented to solve physics problems. So we will have a more physicsy discussion, even though this is a mathematics course. To study vectors in more mathematical, rigorous contexts, I encourage you to take linear algebra and abstract algebra. But we'll just talk about vectors as mathematical objects from, let's say, a point A in space to a point B in space. Here's my vector V. They're typically denoted with an arrow on top or boldface in text. It's really hard to draw bold, so we just put the arrows. A vector is a mathematical object that has a magnitude, like a length. That's what the magnitude is defined as, the length. And we use the Pythagorean theorem to get the length because we're dealing with Euclidean geometry. So in general, we have a vector emanating out of the origin that values x, y. The magnitude of V is going to equal this. It's just an application of the Pythagorean theorem. So it has a magnitude. So in that sense, it's just like a number. Numbers have magnitudes. What is the magnitude of 4? Absolute value of 4. What is the magnitude of -7? Absolute value of -7. 7. They all have magnitudes. But a vector also has another piece of information which makes it interesting, more interesting than just any old numbers. Pure numbers are typically referred to as scalars. Because they scale the vectors, as you will see. And they don't have to be, but for our purposes, our scalars will be elements of the real numbers. Okay? But yeah, these guys have a direction on top of having a magnitude. They also have a direction. This vector is going from A to B. The number 3 isn't really going anywhere. It's just 3. 3 where? Once I say 3 east, 3 miles per hour east, when I assume some direction and the magnitude, then that value becomes a vector. Okay? So it has direction. One way to parameterize such direction is to just say, well, V is equal to a bracket notation. Okay. Just say what its x and y coordinates and rectangular coordinates are using brackets. Another way to parameterize its direction is to utilize angles. So trigonometry will now get utilized with vectors. We'll be using trig in our discussion with vectors. Now, before I dive into that, let's just do some simple geometrical operations with these vectors. And then show how they correlate to algebraic operations. Okay, let's say I have some vector A. Let's say I have some vector B. I can add these two vectors geometrically, like so. You have to do it in head-to-tail fashion. This is the head, this is the tail. So you have to line up one of the vectors, head to tail, head to tail. Okay? And once you do that, you connect the head all the way to the tail to form the new vector, A plus B. You see that? What about A minus B? Well, notice that taking the negative of this doesn't change its magnitude, like we discussed, but it does change its direction. It won't be pointing up anymore. It'll be pointing what? Down. Very good. So to get this, I will get the vector A, head to tail fashion, the vector B, like so, and then I will connect them. Boom. A vector minus B vector. Simple as that. Okay? Just like how we have the number 0, we need a vectorial analog. So we define something called the 0 vector. Okay? Interestingly enough, the book says it is the only vector with no direction. But we define vectors as having magnitude and direction. Isn't that a contradiction? Not really, because its direction is no direction, right? Another way to think about it is the 0 vector is the only vector that emanates in all directions. So both are true. That's all really technical, fancy math, though. All right. At the end of the day, it is a logical vector that we can have, and its representation would just be a dot at the origin. Okay. Just like how we have the number 0, by the same token, we need the vector 0. Now, let's talk about displacement vectors. Have you guys seen this stuff before? You guys haven't seen vectors before?
Well, yeah, vectors.
Vectors?
Displacement vectors, I don't know.
Okay. Have you guys taken physics?
Yeah.
Okay, so we've talked about that in physics. This is looking familiar? Okay, good. A displacement vector is not very fancy at all. Okay. Let's say you have some point 1, 2, and you have some other point 4, 5. A displacement vector is a vector that starts at 1, whichever one you want. Let's say we want to start at the other one, and it goes to the other point. So let's call this P1, P2. This will be the displacement vector, P1, P2, arrow on both. And the way we do that is notice that P2 is second, so it's the final. So P1, P2 vector is defined as, in bracket notation, the final x minus the initial y. This is a 4 here, 4 minus 1, comma, 5 minus 2. So it equals 3, 3. That's what the vector equals. 3 bracket 3. Okay. But I could also create a displacement vector in the opposite direction, P1 to P2 vector. Then we just switch the order in which we do this. This becomes 1 minus 4. This becomes 2 minus 5. And this vector will have values -3, -3. So it'd be a vector just like that one, going in the opposite direction. It starts from here, ends here. Easy as that. Okay. Okay. Aha, now let's talk about scaling vectors. We actually technically already talked about it. Remember when we had that b, and then we said negative b, just, yeah, we scaled that vector by a -1. We multiplied it times a -1, and it scaled it. It did a geometrical operation on it. So let's say we have some vector v, like so. 2v would be a vector going in the same direction, but double its magnitude. Okay. So are you okay? So this is the mathematical symbol for any. It's upside down A. Every time you see an upside down A, when I write it, it just means for any or for all, for any, all. Okay. I'm a mathematician. I'm going to use this notation. Every time you see upside down A, it just means for any or for all. So for all vectors, V, an element of capital V, this is a vector space. Not on the test. Not on the test, but I'd like to tell you that vectors live in vector spaces. You learned that in linear algebra. For all vectors V in a vector space, we may take a scalar S, an element of the real numbers, and create a new vector S times V, having a new magnitude of S times magnitude of V. Okay, so let's apply that to this very simple situation here. This vector V has magnitude V. This vector 2V is double that. So by this, it's absolute value 2 times magnitude of V. And you literally just get this, double it. And with B pointing up, when you multiply it times the -1, it points it downwards. Its magnitude didn't change. That's why we put the absolute value to take away that negativity in the -1. Its magnitude doesn't change, but its direction does. Just like how if I did this a negative 2V, it would have gone like this in the opposite direction. Okay, simple as that. We will not be getting into vector space theory, unfortunately, and we will not be getting to module theory, something I wish I could teach. So, okay, that's implied. Okay, we can define vectors in 3D as well. A vector here. Okay, this is X, Y, Z. Okay, this vector will be represented like this. All right. You'll see what this bracket stuff means here very soon. All right. The book also likes to highlight that, you know, this vector V here, and let's say another vector V prime over here, they're the same vector if they have the same magnitude and the direction. They may not be located in the same spot, but it's like I made a copy of this guy and just picked it up and put it over here. They're the same vector. Your book highlights it there as equivalent vectors. But they do reside in different portions of geometrical space. So, yeah, make sure you take that into account. And notice that we can create three-dimensional displacement vectors. So let's say we have a new situation here where we have, I'll just rewrite it. We can do a 3D displacement. This is some point x1, y1, z1. This is some point x2, y2, z2. I can create a vector from here to here, a vector v, and v would just be defined as in the two-dimensional analog. You get x2 minus x1, y2 minus y1, z2 minus z1. So now you can create a displacement vector that way. And you may be wondering, well, how do these brackets encode the direction? Well, the brackets don't necessarily encode the direction. This is just notation. The direction in which the vector is going is encoded by which number comes first. The x2 comes first, means it's the final destination. The x1 comes second, meaning it was the initial. If we switch their positions, then it would be a vector coming from here to here. And that would be discernible, right? So its direction is encoded in the order in which we subtract. So we talked about magnitude in the Pythagorean theorem in the two-dimensional analog. You can also do it in 3 dimensions, okay? The magnitude of a 3-dimensional vector, x, y, z, v is equal to x, y, and z. Magnitude of v is going to be equal to the square root of x squared plus y squared plus z squared. The proof is very simple. You can create a line here off of the diagonal, okay? Notice that this creates a right triangle, and it has a value x here, and has a value y here, and then it has a value x here, okay? And then we connect it like that. This is your diagonal, D1, and this is a distance 1, and we call this a distance 2. So this is distance 1, and we can solve for distance 1 because distance 1 is equal to the square root of x squared plus y squared, because it is the hypotenuse, okay? So notice that this triangle makes another triangle. Here's the magnitude of v. Here is our d2, here's our d1, and so magnitude of v by the Pythagorean theorem will equal the square root of d1 squared plus d2 squared. And d1 is this, so when we square it, we get square root of x squared plus y squared plus d2 squared. Now all we gotta do is find d2. Notice that it is a triangle that has hypotenuse magnitude of v, upper d2, and over here your d1. So I want to find d2, right? So d2 is going to be equal to the square root of the magnitude of v squared minus d1 squared, okay? So you can eventually, through this line of reasoning, derive this, all right? notice that D2 is Z itself. You see that? This distance from here to here is Z, because you measure it as Z. So I don't even have to make it too complicated over there. I can just replace D2 with Z, and you would be done. Okay, this isn't on the test. This is just for your information. It's a derivation of the three-dimensional magnitude. I like to give extra details because for me, the extra details allow me to understand it more. But I understand not everybody likes extra details. And so when I show them, I will make sure to disclaim that, you won't be asked to derive this on a test. But understanding how it's derived will make you understand Calc 3 on a much more deep level, on a more fundamental level. So it's worth talking about once in a while. So we talked about subtracting vectors. We already talked about that. Now let's talk about the vector axioms. Okay. Let A, B, C be vectors. And let C and D be scalars, real numbers. We have the following axioms. We have the first axiom that vector A plus vector B, it would be the same as vector B plus vector A. This is called the commutative property of vector addition. Another property is that A plus B plus C, parentheses on the B plus C, meaning order of operations, we add these two first, then add it to A. It would be the same result as adding A and B first, and then adding C. It's an order of operations. This would be added to that, you get a result, versus now these two combine, then add to that. This axiom states that it doesn't matter. This is called associativity of the addition of vectors. Now we have this property that any vector added to the zero vector is itself. This is called the additive identity. Because when you add this vector, the zero vector, to any vector, it just reproduces itself. Kind of like when you add 0 to any number, it will just reproduce that number. 0 plus 3 is 3. 0 plus 9 is 9. There's a fourth property. This is called the additive inverse property. Any vector added to its negative gives you the zero vector. Time for another property. This is the scalar distribution property. It says that a scalar multiplied times the addition of two vectors is the same thing as the scalar times the vector added to the scalar times the other vector, and then you add them. So it doesn't matter whether you add the vector first, then scale, or scale, then add. You get the same thing. Property 6. We have two scalars added times a vector. This property states that whether you add the two scalars and then scale the vector, or whether you scale the vector then add, it doesn't matter. You get the same thing. So this means numbers can distribute across vector addition, and this means vectors can distribute across scalar addition. Remember, scalars are just real numbers. Pi, 14, 36. These can all be found in your book. This is not extra information. Okay, so another one is now and we talked about the rules of addition. What is the rules of multiplication? So my C needs to not look like the parentheses. Okay, so C multiplied times D, quantity, times the vector A. This is multiplicative associativity at its finest. It's saying, you know what, it doesn't matter whether you multiply C and D, then scale the vector. Or if you say, well, let me scale the vector by D, and then scale it by C. Doesn't matter, you still get the same thing. And last but not least, this is called the multiplicative identity. The number 1 times any vector is itself. So, yes, notice that's the number 1. There is no, vector 1. Because they call it a vector 1, it needs a direction. 1 can't alone be a vector. The number 1 is a scalar. But this is saying whenever you scale a vector by 1, it is unchanged, right? Aha! Now I'm going to explain to you something that will allow you to understand these brackets, these darn brackets a little bit more that we've been throwing around here. And if you take linear algebra, you'll definitely be talking about basis vectors more. Okay, so let me introduce to you the basis vectors I, defined as this vector, J, defined as this vector, and K, defined as this vector. Notice that these new guys have a new notation. They have a hat. That new notation is to distinctify them. Is that even a word, distinctify? To allow them to be distinct, to distinguish is what I'm trying to say. To distinguish them as being basis vectors. Basis vectors are vectors of magnitude 1, as you can use the Pythagorean theorem or the magnitude theorem to see that they have magnitude 1. And these vectors allow you to build every other vector. And you'll see what I mean by that. That's why they form a basis. Here's your x, here's your y, here's your z. This is I hat, j hat, k hat. Okay? These vectors allow you to build all other vectors because all vectors are a linear combination of these vectors. So let's say I have some arbitrary vector v coming down here, y, z. V we were writing was equal to bracket x, y, z. But this bracket notation really also means that it's the number a times I hat plus the number y times j hat plus the number z times k hat. This bracket notation and this basis vector notation are the same thing. I prefer the bracket notation because it's less writing and I'm lazy. But whenever you have this bracket notation, you can always break it down into the IJK formulation. So let's, for example, let's say A is equal to I hat plus 2j hat minus 3k hat. And let's say B is equal to 4I hat plus 7k hat. What is 2A plus 3B? Question mark. I'll show you two ways to do it. Here's my favorite way, because it's less notation. I just write this as 1, 2, -3. I just write this as a 4, a 0, and a 7. Because there's no j hat. The entry for j is 0. Okay. Then that means 2a plus 3b is equal to 2 times this plus 3 times this. And by the vector axioms, we know that a scalar distributes. Boom. Okay. And then you just add them component-wise. So this becomes a 14, a 4, and a 15. Another much more tedious and laborious way to use it is notice this formulation, as it is highlighted over there. You can say, well, this 2a is the same thing as 2 times I hat plus 2j hat minus 3k hat. And I'm going to add it to 3b, which is the same thing as 3 times this 4 I hat plus 7k hat. And so when I add these two, let me first distribute. This is 2 I hat plus 4j hat minus 6k hat. This is then equal to 12 I hat plus 7k hat. When we add these two, we just combine like terms. We combine the i's with the i's, the k's with the k's, and the j's with the j's. And it's really what we're doing over here. It's just more, the notation is more tedious. But notice when we do it, we get 14i plus 4j. I did not multiply the 7 times 3. Yeah, I know. So then I get 15. Okay. Notice these are the same answers. So however you do it, tomato, tomato, potato, potato, it don't matter. See, it's the same thing. I like this way, it's faster. You less writing. Now, let's talk about unit vectors. These I, J, K vectors we've been talking about, I, J, and K, they are not only basis vectors, but they are also unit vectors. What is a unit vector? A unit vector is a vector of magnitude 1. That's it. It can go in any direction it wants, just as long as its magnitude is 1. Notice that I, J, and K are all unit vectors. For instance, I'll show you how I is a unit vector. I hat, magnitude of I hat is the square root of 1 squared plus 0 squared plus 0 squared, which is square root of 1, which is 1. Aha, it's a unit vector. Right? I can do the same thing for J and K. All right? So, that's trivial, but here's a non-trivial example. We can construct a unit vector out of any vector. No matter what the magnitude of the vector it may be. It can have magnitude 17. We can make it into a unit vector. Okay? So for some arbitrary vector, for any vector v, let's define it as x, y, z, we can construct a unit vector u just by doing this. U sub v or we just call it U, we've defined it to be a unit vector, is equal to 1 over the magnitude of V multiplied times the vector V. Prove. I will prove to you that this is indeed a unit vector, 1 over magnitude of V times V. Notice that 1 over the magnitude of V is 1 over square root of x squared plus y squared plus z squared. And that times the vector V looks like this. And so when I multiply, I get this. Okay? But I'm trying to prove it's a unit vector. So I have to take its, I have to take the magnitude of this. So once I take the magnitude of that, really, I just get one giant square root. This thing squared plus this thing squared plus this thing squared. Can everybody see? Notice that when we square this, we get the square root of x squared all over x squared plus y squared plus z squared plus y squared all over x squared plus y squared plus z squared plus z squared all over x squared plus y squared plus z squared. Moving the calculation over here. I can factor out that x squared plus y squared plus z squared out of each term. So I get 1 over x squared plus y squared plus z squared times x squared plus y squared plus z squared. Notice they cancel. And you take the square root of 1. Proof is completed. QED stands for quod erat demonstratum, which is Latin for thus it has been shown, or thus it has been demonstrated, or thus it has been proved. So now that we've proved it in general, it is quite trivial to do a example with numbers. But as trivial as it may be, it's part of my job to show it. So I'm just going to invent something. Or, yeah, I just invent it. Let's pick easy numbers. Let's say V is equal to 1, 2, 3. Find U. Well, that process shows us that U should equal 1 over the magnitude of V times the vector V. What is the magnitude of V? It's this times the vector V. Right? What's inside the radical? That's 1 plus 4 plus 9. What's this end up becoming? 1 plus 4 plus 9 is what? 14. So I distributed 1 over 14 square rooted. That would be our unit vector right there. What? What is that you say? Oh, you wish for me to provide justification for my assertion? Okay, I'll prove to you this is a unit vector. All I got to do is take its magnitude. What is the magnitude of this? Well, you just take each entry and square it and put a radical. This should equal 1. Let's see. 1 over 14, 4 over 14, 9 over 14. They all have a common denominator. We can combine the top. Aha! I see a head nod. So on a test or whatever, homework, whatever, you want to check whether your answer is correct. Do this. If it doesn't equal 1, you did a calculation error. Now let's do a physics problem. Man, I'm always just a little scraggling because of the syllabus. The syllabus got me scraggling. I'm not going to be able to fully get through this, but I'll set it up. So we have this very lightweight, 100 pounds, hanging from the top of a roof or a ceiling, like so. And we wish to calculate the tension in the ropes or the wires or whatever. You guys taking physics? You've done these before? Okay. Yeah, it's just like that. There's going to be a T1, it's a vector. There's going to be a T2, it's a vector. Okay, notice by alternate interior angles that if this is 50, then so is this. This is 50 degrees. So we can construct this triangle, where this is your T1. This is your what I like to call T1 of X, and a T1 of Y. Okay. Okay. And over here, we can do the same thing, utilizing alternate interior angles. We can construct this situation where this is a 32 degrees. This is your T2, T2 of X, T2 of Y. Okay. Then we apply sine and cosine. All right, here's the fundamental assumption. And this is actually in your text. It's the last part of your text. So I'm not too worried that I won't be able to go over all of it. The fundamental assumption is that the tension in the wires equals this measly 100 pounds. It's not that heavy. So then all you do is you do trigonometry and solve. So I don't have time to go over that, but I will next class if you so desire. But really, all you do is apply sine and cosine to 50 and 32. Okay. Sine of 50 degrees would be opposite over hypotenuse. And then you can solve for T1. And then cosine of 50 would be adjacent over hypotenuse. And again, you can solve for T1. Do the same over there. Solve, and you'll be done. Notice that the key here is that we can solve for one of these. Let's say T1. Magnitudes, by the way, these need to be declared that these are magnitudes. The magnitude of T1 would just be 100 measly pounds minus the magnitude of T2. So then you can apply those and plug them in. This is in your book, so I don't feel super bad about not covering it today. It's the dang syllabus last time, you know. It got me just one increment behind. And so now I'm just one increment behind, and then one increment behind. And yeah. So. But the solution is in your book, so I don't feel that bad. Matter of fact, maybe deep down inside, I knew that I should use that example. Because if I don't get to it, you guys could just read it. That would be very clever of me, wouldn't it?
You would.
Alexis, have you been listening? Type in if you've been listening. Oh, she said yes. Hi, Alexis. This is cool that you can attend lecture virtually. That's wonderful. I wish that technology was around back when I was a student, so I wouldn't be driving 100 like down expressway trying to get to class.